We are looking at, this is in-class activity review, going through working with these limit problems that are in the form of piecewise function. And let's look at number 1 here. This first piecewise function, we have a graph that exists to the left of -4. We have another piecewise function that exists between -4 and 3. And then finally, a third graph that exists to the right of 3. So we can think of it as, there are 3 divisions with these with these 3 graphs. Now, these 3 graphs may or may not connect with each other, and but we're going to have to determine that algebraically as we try to find the limits for each of these problems. So for part A, it says limit as x approaches -infinity. So the first thing we do is we look at the location where the limit is referring to, and then that will help us to narrow down which piecewise function to look at. So if we're approaching -infinity is going to be to the left of -4, so it's going to be in this region, or it's going to be to the left, or in this third region here, or this furthest left region, which is going to refer to this x plus 2 and x squared minus 4. So we can do limit as x approaches -infinity. So that's this condition is going to affect this first piecewise function. So now we can treat this like algebraic problem, right? So if we're approaching negative or positive infinity, we want to think of this as finding horizontal asymptotes, which means we want to compare degrees between numerator and denominator. So notice that the denominator has a higher degree than the numerator. So whenever that's the case, and if we're approaching infinity or negative infinity, the limit will always go to 0. Okay. For part B, limit as x approaches -4 from the left side of -4. So if we're approaching -4, we have 2 functions that are involved, but one graph is to the right of -4, so in this region. And then in the first piecewise, it's going to be to the left of -4. So we see the one-side limit. We're approaching -4 from the left side of -4. So we know that based off of this information, we know we're referring to this first piecewise. So limit as x approaches -4 from the left side of -4 is referring to this first branch, x plus 2 over x squared minus 4. So now we just treat this like an algebraic limit problem. So the first thing we always do is we always plug in our target x value and see what number we get. So if we plug -4 in, we get -2. -4 in the denominator, when we evaluate that, we get 12. So -2 over 12 gives us a real number of -1/6. So that's our answer. That's our limit. That's our one-sided limit. Okay. For part C, we're approaching -4, but this time we're approaching from the right side of -4. So -4 is right at the boundary between the first and second piecewise, but we're talking about from the right side. It's not very clear here. That's a plus from the right side of -4. So from the right side of -4, it's going to be in this region. So the second piecewise function. So we're going to put down the second piecewise, since that is where the graph is coming from, is affecting. So if we're approaching -4 from the right side of -4 of x plus 3, we plug in our x value, and we get -4 plus 3, which is -1, so that's our real number. Now, notice that when we use one-side limit is helpful in terms of determining which piecewise function that we're referring to. But once we do that, then our next step is just to plug in that x value. We're going to ignore that one-sided limit. The one-sided limit is not going to take effect algebraically unless we get some sort of indeterminate form. I'm sorry, if we get undefined, then we have to decide whether the graph is approaching positive or negative infinity if we're approaching an asymptote. Okay, for part D, limit as x approaches 4. Now, notice that the graph is split on either side of -4. I'm sorry, on either side of 4. So if we're approaching limit as x approaches 4, I'm sorry, from x approaches 4 is purely going to be to the right of 3, so we're just talking about this function here. So limit as x approaches 4 is going to be in this region, and it's not going to be at an endpoint. It's not going to be at a point where the function could potentially be split between two piecewise. So as we're approaching 4, it's squarely in the middle of within this function. So we can just plug in, we can just use this function. So if we're approaching 4 of x cubed over x minus 5, we plug in 4, we get a real number. 64 over -1 is -64. Okay. If we're approaching 5 from the right side of 5, so 5 from the right side of 5, everything to the right of 3 is going to be referring to this third piecewise function. So we can just look at this function here. So if we're approaching 5 from the right side of 5, we plug in that 5 first. We're going to ignore that one side limit because if we can get a real number out of plugging in 5, then we don't have to worry about anything else beyond that. But if we plug in 5, we get 5 cubed, which is 125. Plug in 5 for the denominator, we get 5 minus 5, which is 0. Now 125 over 0 is undefined, right? The limit does not exist. This is not a real number. But we're not asking for a limit. We're asking for the one side limit. So basically what's happening is there's a vertical asymptote here. And because 5 is causing the denominator to be 0. But it's asking what is the behavior of this undefined limit from the right side of 5. So basically, what is the graph doing if we're following the right branch of the graph? So if we're following the right branch of the graph, if it's approaching a vertical asymptote, there's only two options. Either the graph is going to shoot up to positive infinity, or it's going to go down to negative infinity. So the way that we can determine this algebraically without having to look at a graph is we choose a decimal value that is relatively close to 5 from the right side of 5. So if we're choosing a decimal within a tenth from the right side of 5, we can choose 5.1. So all we care about is, does 5.1 going to give this expression a positive or negative number? If it gives us a positive number, then we know that it's inching towards positive infinity. If it gives a negative number, we know that it's inching towards negative infinity. So if we plug in 5.1, 5.1 cubed is going to be a positive number. 5.1 minus 5 is also going to be a positive number. So positive over positive is positive infinity. So we know between these two choices we can narrow down that the one side limit as we approach this vertical asymptote, this branch on the right side of 5 is going to go up to positive infinity. Okay, for f, as we approach positive infinity, we know that this tells us we're talking about this condition to the right of 3. So we're just looking at x cubed over x minus 5. So if we're approaching infinity, we can think of it again as looking at in terms of horizontal asymptote. So we compare degrees between numerator and denominator. Numerator is going to win out, has a higher degree. So if we plug in a large positive number, we see that it's going to go to positive infinity. So we know it's going to go to infinity. We just have to decide whether it's going to go to positive or negative infinity. If I plug in a large positive number in the direction that it's headed towards, I'm going to get a positive over positive, which will ensure that we did get the sign correct, positive infinity. Okay, for g, limit as x approaches -4. So we know that what's happening is at -4, we have piecewise function that is split on either side of -4. So in order for us to determine whether the limit exists, we need to know, is the graph going to approach the same y value on either side of -4? We actually found this information from part C and D. As we approach -4 from the right side of -4, we see that the y value, the graph is approaching a y value of -1. But on the left, from the left side of -4, we see that the graph is approaching -1/6. So we see that at -4, there's a disconnect between these two branches. So that tells us that the limit does not exist at 4. So because the one side limits do not agree, we know the limit doesn't exist. And then finally, h of -4. h of -4 is asking for the order pair. Order pair is going to exist where the graph has a line underneath where there's a where it's less than or equal to or greater than or equal to. So we see that is with the second piecewise. So if we plug in -4 into the second piecewise, -4 plus 3 is -1. So we see the order pair exists at -1. Okay, these two problems on the back is using continuity condition. Use continuity condition to determine if the graph is continuous. If not continuous, determine if we have removable or non-removable discontinuity. So we have a piecewise function here. Without graphing, we're trying to decide whether there's a break in the graph, and if there's a break, what type of break do we have. So just to review continuity conditions, first thing we do is we identify what our C value is. We identify where the potential break point is, and usually the problem should be pretty straightforward in terms of identifying that information. So if we look at number 2, we see the potential break is at 4, so the C value is 4. For 3, we see the potential break in the graph is at -1, so the C value is -1. Okay, so back to the definition here. F of C has to exist, so if we plug in C into the function, the point has to exist. Okay. The second condition is, does the limit exist? So at that C value, is the graph going to, are the branches going to connect to the same Y value? Sometimes it's just a matter of finding the limit of that function, but if it's a piecewise function and the piecewise function is split on either side of C, then we have to go through the additional step of finding these two separate one-sided limits and comparing them to see if they agree, see if they approach the same Y value. If they do, then we know the limit exists, but if they don't, if the one-sided limits do not agree, or if the limit does not exist outright, then we know that it fails the continuity condition, and the type of discontinuity is called non-removable discontinuity. And non-removable discontinuity is true if the second condition fails. Right. So let's say the point exists and the limit exists, and then we're moving on to the third condition. So the third condition, we test if it passes the first, if it passes the second condition, and this is saying that f of c equals the limit as x approaches c of f of x. So that simply tells us to compare the results between the first two conditions. If the point exists and the limit exists, we want to know, do they agree at the same point? If they do, then we know the graph is completely continuous through that point. There's no hole, there's no break, there's no jump discontinuity. The graph is going to continue through, so we can visually sketch that graph through that point without having to lift up our pencil. However, if the third condition fails and it passes the first two, then that tells us that the point exists, the limit exists, but they don't agree at the same point. So what that tells us is that there's a hole in the graph, and if the third condition fails, what the type of discontinuity we have is a removable discontinuity. Okay, so let's look at number 2. F of x equals x squared minus 3 to the right of 4, and we have x plus 1 over x squared plus 1 to the left of 4. So we know the x value in question is at 4, so we go through our first condition, f of 4. F of 4 exists where we see a less than or greater than equal to, and with an inequality with a line underneath. So we pick the first piecewise to identify the order pair. F of 4 is 16, which is 4 squared minus 3. 16 minus 3 is 13, so it passes the first condition. We know the graph is physically at the y value of 13 at 4. So now we need to find the limit. Now we need to rely on two separate limit statements to find this, because the graph is split on either side of 4. So we can't just find the limit of one function and find the limit for this overall function. We need to evaluate the limit from the right side of 4 for this function, and also evaluate the limit as x approaches 4 from the left side, since this graph is existing to the left of 4. So I'm going to set up two separate one-side limit statements. One is from the left side of 4, which is the second piecewise, and then from the right side of 4, which is the first piecewise. So we're going to do this algebraically. I'm going to plug 4 into the first piecewise. I get 4 plus 1 is 5. 4 squared plus 1 is 17. 5 over 17. So from the left side of 4, the graph is approaching a y value of 5 over 17. But from the right side of 4, if I plug in 4 in for x squared minus 3, I get 16 minus 3, which is 13. So we see that the one side limit do give us two separate y values. So that tells us the second condition is going to fail because the one side limits do not agree. From here, we know what type of discontinuity we have. We have a non-removable discontinuity since the limit does not exist. And we're able to answer the question and also identifying the type of discontinuity. Number 3, we have a piecewise function. So we want to identify our potential x value in question, which is at -1. So -1, let's first find the ordered pair. So f of -1, we see that this piecewise function is for all x values that's not -1, and this piecewise is for just -1. So we know f of -1 is 3 just by looking at the second piecewise. So this is simply just a point on the graph. The second condition is evaluating the limit. Now notice that these two piecewise function is not split on either side of -1. This function is going to apply for everything that's every x value except -1. So to the left of -1 is this function applies. To the right of -1, this function also applies. The only time this function does not apply is at -1. So really, this second piecewise is just a point on the graph. And then the rest of the function is taken care of by this first piecewise. It's basically saying all real number except -1. So everything to the left of -1 and everything to the right of -1 is going to be handled by this first piecewise function. So in this case, there's no need to go through one side limit because we're talking about the same function. I mean, we could evaluate one side of the limits, but we would be doing it with the same function. So we might as well just find the limit once just for this function, since we're not having to deal with two separate functions on either side of -1. So we just go ahead and write this down. Write limit as x approaches -1 for our function in question, and if we plug -1 in, we get 0 over 0. But if we reevaluate, meaning that we factor the numerator, we get the numerator's denominator to cancel out, and if we reevaluate the limit, we get -1 minus 1, which actually should be -2. Okay. Now we see that the point exists, the limit also exists. However, the third condition is where this continuity condition is going to fail. The condition 3 fails because 3 does not agree with -2. So we see that the point does not exist where the limit is. So because the third condition fails, we can say that there's a removable discontinuity at x equals -1.